Welcome. We are at a point now where we are able to find all zeros of a polynomial, and there is a linear factorization theorem that says an nth degree polynomial has n zeros, provided we're allowed to use complex numbers, imaginary numbers in there. So we expect to have 3 of these. I know a third degree polynomial rises to the right, falls to the left, so there has to be a real zero. So if we didn't have a graphing calculator at our disposal, then we could try to factor this. This doesn't look very convenient for factoring by grouping. You can give that a shot. Or we could use the rational zero test, which says we would take all of our factors of 6, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, and try all of those over all of our factors of 5, plus or minus 1, plus or minus 5. And to be honest, that's not too bad of a list compared to what we might get. The problem is the the rational zero test does exactly that. It tells us the possible rational zeros. There may not be a rational zero, and the only way you understand that is if you understand that a rational number is a number can be written as fractions of integers, but real zeros have square roots and things like that in them. Maybe this cubic has a square root type zero. So maybe none of these factors over these factors as a fraction work. So we'd synthetically divide that and hope we came up with one. So as an option, we could go to our graphing calculator. I'm not bitter about it. I didn't used to get to do that. I'm an old guy, and we had to go through these rational tests and just hope that one of them was. And if it wasn't, then we had to start trying to just narrow down zeros by graphing tons and tons of points. You guys have it pretty good. Now, forgive me, I'm going to have to jump back and forth between programs. So I'm going to take number 25, keep those intact. I'm going to pull this program up, and I'm going to ask for it to give me that function, number 25. There's the function we're working with, and I'm going to go ahead and graph that, as you might be doing it on your graphing calculator at home. I'm going to do this as a Zoom standard. So negative 10 to 10. And I see, well, I got a 0 there for sure, but boy, it doesn't show me much about the graph. So on your calculators at home, you might want to do an auto fit or a zoom fit, where I zoom fit this guy and I say, okay, my zero's in here somewhere, but it's hard to tell because I'm going up to almost 5,000 down to almost 7,000. It's hard to tell. Maybe there's 3 zeros in there. So I see all my zeros appear to be maybe between negative 1 and 2. So I'm going to x min x max this from negative 1 until 2. And then I'm going to zoom fit again. Stretch the graph out. Let's see. Okay, now I see. I've got 1, 0. Some wiggling's going on over here, but I definitely have 1, 0. It appears to be over here somewhere just to the left of 0. So I test for 0. There's a value near 0, and it tells me the 0 is negative 0.2, and you could do that second calc 0 on your calculator. That is definitely rational because before we were allowed to call that negative 0.2 and be lazy, we would have had to say instead of 0.2, we would have had to say 2 tenths. 2 tenths, 1/5. That's an integer over an integer. That's the very definition of a rational number. So I'm going to synthetically divide negative 1/5. Okay, so back to here. We're going to go from our current slide. And now I'm going to synthetically divide negative 1/5. Notice negative 1/5 would have been one of my choices for a rational zero. So I'm just going to be really clever and I'm going to say, you know what? I'm feeling lucky today. I'll bet negative 1/5 works. Sure, I could have tried easier ones, but I just feel like maybe that's a special one. 5, negative 9, 28, 6. Bring down the 5. 5 times negative 1/5, negative 1. And negative 9, negative 10. Times negative 1/5, positive 2, plus 28, 30. Times negative 1/5, negative 6. Holy cow, wasn't I lucky? So, excuse me, negative 1/5 is a 0, which means that x plus 1/5 is a factor. So right now, if I was to factor this, I could write it as x plus 1/5 times 5x squared minus 10x plus 30 and we notice that 5 can be factored out of this guy. And I could put a 5 in front of here, but I think I'm going to just go ahead and run that 5 right through this factor to clean it up a little bit. So now I have factors of 5 times x plus 5 times 1/5 1. And if I factored out the 5 and gave it here, I would be left with x squared minus 2x plus 6. And now we would try to factor that quadratic. But if we looked at the graph, there were no more real zeros. I don't expect that to factor. Are there factors of positive 6 that add up to negative 2? I'll claim no. So we can go to quadratic formula to try to solve this. So quadratic formula would give me the opposite of b, 2, plus or minus square root of b squared, that is negative 2 squared 4, minus 4 times a 1 times c 6, so minus 4 times 1 times 6 minus 24, all over 2a, 2 times 1, 2. That gives me 2 plus or minus square root of negative 20 on 2. And you say, oh, we don't have any zeros. Well, once again, we knew that when we saw the graph. The graph only had 1 0. It only had a 0 at negative 1/5. Okay, but we're allowed to be in imagination land now, so we can go ahead and pull out the I out of negative 20, the square root of negative 1. This becomes 2 plus or minus. I'm going to get an I. But the square root of 20 can be broken down into square root of 4, 2 times square root of 5. And that reduces into 1 plus or minus, divide the top and bottom by 2, 1 plus or minus I root 5. And the standard form up top here is a plus bi. So you're going to see this oftentimes written as 1 plus or minus square root of 5i. And I'm not crazy about that unless you're really careful to separate the I from the square root. So if you were going to write it that way, it should be square root of 5, and make sure the I has a nice gap in there. That's why I put the I in front. The I is definitely not under the square root. Okay, that means my zeros are 1 plus or minus I root 5. My other zero we already found is negative 1/5. And my linear factors become 5x plus 1 times x minus this guy, 1 minus I root 5. So that is x minus 1 distribute minus I root 5 times x minus this guy. I'm going to do the minus part of it now. X minus 1 distribute the negative plus I root 5. So linear factors. Why are they called linear factors? Because this is x to the first, and x to the first. Those are linear terms. These just happen to be linear complex. Okay. Number 36. Find all zeros of the function and write the polynomial as a product of linear factors. Same type of problem again. Again, I'd love to factor this if I could. Nothing jumps out at me right here. So I could list all the factors of 16 on all the factors of 1 and start trying to start trying the rational zero test, start trying to synthetically divide those things. But I'm going to, again, escape out of my program, go back to my calculator, and I'm going to ask for number 36's function, and you could graph this at home on your calculator. So there's our function that we were dealing with. I'm going to graph it, and I'm going to go straight to Zoom Standard and work from there. So on my graphing calculator, I would probably be now just typing Zoom Standard. So I do an auto domain negative 10 to 10. So there's our function. It appears like we have a 0 at 4. I know that maybe I'm going to run from negative 4 to 6 here. Let's give this a shot. Negative 4 to 6, because maybe there's some more zeros somewhere else out there. But if I go zoom fit, let's see. Okay. I think I'm going to set my Y max maybe to be, actually, maybe I'll set my X min to be negative 1 over here, because I don't have any zeros to the left of negative 1. Negative 1 and zoom fit again. Big fan of zoom fit. Okay, so I see I have zeros over here near 4, and if I guess a 0 at, say, my 3.2, it tells me that my 0 is 4. Okay, here's a big key on this one. Might I have zeros somewhere else? I'm going to claim no because we've got a lot of wiggling going on here. There's a potential double 0, and here's the other wiggle of r to the 4th. That graph is pretty well spent. From that point on, it's going to rise to the right, rise to the left. But as I said, the important thing to notice here is 4 might not only be a 0, 4 might be a double 0 because this thing's trying to act like a parabola for an instant right around 4. But 4 is definitely a 0, which means at least once I can synthetically divide 4 through this guy. So here we go. That is 1x to the 4th minus 8x cubed plus 17x squared minus 8x plus 16. No holes in that. In other words, I have a x to the 4th, x to the 3rd, x squared, x to the 1st, x to the 0th term. We decided we're going to try to run 4 through that. Of all the choices, I'm feeling lucky with 4. 1 times 4, add them, negative 4 times 4, negative 16, add them, positive 1 times 4, 4, add them, negative 4 times 4, negative 16, and once again I got lucky. But remember the shape of the graph at that 4. It looks sort of parabola-like. Maybe I can run 4 through this again. I wonder. Maybe the graph back there went through 4, went down through the graph, and came back up through 4.01. I don't know. Let's find out. Bring down a 1 times 4, 0 times 4, 0 plus 1, 1 times 4, 4, and sure enough, it did go through there twice. So right now, I have this thing factored as x minus 4 squared, and I'm left with an x squared plus no x's plus 1. X squared plus 1. And I'd love to get this guy factored. But I can't factor the sum of perfect squares over real numbers. So what if I just said this? What if I said x squared plus 1 equals 0? We could quadratic formula that, but what a waste of time. X squared equals negative 1. X equals plus or minus square root of negative 1 or plus or minus I. So my zeros are 4, and that is a multiplicity to 0. And plus or minus I. There's my 4 zeros that the linear factorization theorem guaranteed that we would have. And factored as linear factors, x minus 4 times x minus 4 squared, and x minus positive I, and x minus negative I. So there we have it. Graphing calculator, pretty handy. Again, if we didn't have it, we'd have to just start running through all of our factors of 16 divided by all of our factors of 1. Eventually, we'd try 4, and then we'd have to ultimately try 4 again. So love those graphing calculators. Okay, find a polynomial function with these zeros. Here's a beautiful formula. Simple, simple, simple to understand. One of the blue boxes in our books. The title of it is Complex Zeros Occur in Conjugate Pairs. And then they go on to explain it, but they don't need to. If this is a 0 and it's a complex number, its conjugate is a 0, 2 minus 5i. And we're supposed to find a polynomial function with those zeros. So my polynomial, if negative 1 is a 0, x plus 1 is a factor. If negative 1 is 0, x plus 1 is another factor. If 2 plus 5i is a 0, x minus it, x minus 2 distribute minus 5i is a factor. If 2 minus 5i is a 0, then x minus that, distribute, minus 2 plus 5i is a factor. And to be honest, we found a polynomial function that has those zeros, but we would at the very minimum FOIL this out because we have conjugate goodness going on there. So I'm going to write this as x plus 1 squared, and I'm going to start foiling, and there's shortcuts to this, but I'm going to go through this the safest way possible, and that is super FOIL. So x times x, x squared. minus 2x plus 5xi. Now I'm going to take the minus 2 through. Minus 2x plus 4 minus 10i. Now I'm going to take the minus 5i through. Minus 5ix plus 10i. And this is minus 25i squared. Minus 25i squared. Ran out of room a little bit there. Okay, so at that point I'm looking for common terms to combine, and I expect good things to happen. I see x squared. That's all I've got for x squareds. How about minus 2x? I've got minus 2 more x's, minus 4x. How about plus 5x's? Minus 5x's cancels. That's the conjugate goodness. How about, I'm going to jump over to minus 10i. Plus 10i, good. What am I left with then? I have this 4 and this minus 25i squared, but that's minus 25 times negative 1 plus 25. And we get plus 29. Now, simplified at this point is in the eye of the beholder. Is this simpler than foiling this out and distributing and superfoiling the result of that out? That one's kind of a toss-up, but I don't think there's any argument that this is simplified compared to that. So if you want to superfoil the rest of this, be my guest. Okay, terminology gets in our way on this. Irreducible over rationals. That is like traditional factoring. Can we traditionally factor? So they are giving us that this is one of the factors of f. And if x squared plus 4 is a factor of f, then I know that x plus 4, or x squared plus 4, could long divide x to the fourth minus 3x cubed minus x squared minus 12x minus 20 and work out evenly. And you'd say, well, I prefer synthetic division. So do I. I cannot synthetically divide with the squared here. I could try to factor that. In fact, you may be working ahead of me here and say, well, that factors into x plus 2i, x minus 2i. You could synthetically run 2i through this and then negative 2i through this. In that much time, I might be able to do the long division. Okay, one thing I'm going to do, though, is when I'm dividing by x squared plus 4, there is a hole there, so this is x squared plus 0x's plus 4. People are pretty good about filling their hole inside the f of x term inside the division, but we ought to go ahead and put it out here as well. I think that helps. So we ask ourselves, excuse me again, x squared, how many times does it go into x to the fourth? X squared times. And I like putting x squareds over x squareds. So I get x to the fourth plus 0x cubed plus 4x squared. But then what do? We subtract those. So opposite sign, opposite sign, opposite sign. And I get x to the fourth minus x to the fourth, 0. I get negative 3x cubed, and I get minus 5x squareds before I bring down a minus 12x. How many times does x squared go into negative 3x cubed? Minus 3x. So that is minus 3x cubed. That is plus 0x squared. And that is minus 12x. And I get, before I do anything, we change that to subtraction, so this becomes plus, plus, plus. I get negative 5x squared plus 0x, bring down a minus 20, and I see that x squared goes into negative 5x squared minus 5 times. Minus 5x squared plus 0x, and minus 5 times 4, minus 20. But of course, we're going to subtract this, so plus, minus, plus, and we end up with 0, as we expected. So I might clean some of this up in just a moment here, but for the time being, I know that I have factors of x squared plus 4, here's a, times x squared minus 3x minus 5. And I said factoring over rationals is traditional factoring. Can I factor this traditionally or without introducing i's? No, we can't factor the sum of perfect squares. Can we factor this? Perhaps. Are there factors of negative 5 that add up to negative 3? No. So I'm going to take just a moment here, clear up just a little bit of space for myself. And we're going to continue on by factoring over real numbers. What do real numbers introduce to us that rationals don't provide or don't give us access to? Well, pi, but I don't think we're going to have pi involved with this. Square roots. Square root of 7 is a real number, not a rational number. So we're allowed to have square roots. Well, I still can't factor anything here, but maybe x squared minus 3x minus 5, if I set that equal to 0, maybe I could handle it through quadratic formula. Let's give that a try. Opposite of b, plus or minus square root of b squared, that's 9, minus 4 times a, 1, times c, negative 5, and I get, that's 4 times negative 5, negative 20, so that becomes plus 20 here. All over 2a, that's just 2. So that is 3 plus root 29 and 3 minus root 29, all on 2. So ugly zeros, but zeros nonetheless. Therefore, if I'm allowed to use real numbers, I can now factor this into x squared plus 4 times x minus 3 plus root 29 on 2 times x minus 3 minus root 29 on 2. That's some ugly factoring there, but it's factoring. And now I get to go over completely factored forms, which means now I can use i's. So if I take my x squared plus 4, I'll put it up here. X squared plus 4, set that equal to 0. I get x squared equals 4, negative 4, excuse me, that's important. Or x equals plus or minus square root of negative 4, that is 2i. So x squared plus 4 can factor into x minus 2i times x minus negative 2i. And then, I'm going to cheat here, add those factors right in here. And we've got this thing completely factored into linear terms. Linear? Yes, because this is x to the first, x to the first, x to the first, x to the first. So terminology gets us a little bit. We need to be able to distinguish between rationals, reals, and complex numbers. And finally, use the given 0 to find all the zeros of the function. So we got this function here. We might be able to try to factor that by grouping. Doesn't look very promising. But they tell me one of the zeros is 5 plus 2i. But they didn't really tell me one of the zeros was 5 plus 2i. They just told me that two of the zeros, one is 5 plus 2i, the other is the conjugate. Remember, one of my favorite blue box, easy to understand rules. Complex zeros occur in conjugate pairs. Therefore, a linear factor of this would be x minus this, which becomes x minus 5 minus 2i, times x minus this, which becomes x minus 5 plus 2i. I'm going to superfoil that out. I'm going to shortcut this. Yes, you could get 9 different terms and combine as I did earlier in this video, but I'm going to get an x squared. That's the only place I'm going to get x squareds. I'm going to get minus 5x and minus 5x. That's the only place I'm getting plain old x's. My two i's are conjugates, so I get plus 2xi minus 2xi cancel. I'm going to end up getting, ultimately, I'll put it over here, a plus 25, and I'm going to ultimately get a minus 4i squared. That's 25 plus 4 plus 29. And everything else will cancel. Now, that is a factor of this, which means it will evenly divide it. I got a shortcut for you here, though. Yes, you could long divide this guy into there and find your last missing factor. But if x squared minus 10x plus 29 is a factor, this is a second degree. I need something to multiply by it to be a third degree. This must be a first degree. It's a linear. It's linear. And the only place I'm going to get, once I put a linear term in here, ax plus b, the only place I'm going to get a linear term in there, or excuse me, the only place I'm going to be able to get x cubes is by putting in x here. So x squared times what is x cubed? X. The only way in this superfoiling I would get a constant would be with 29 times whatever's here. So 29 times what is positive 87 plus 3. So use the given 0 to find all the zeros of the function. Have we done that? Yep, here's a 0. 5 plus 2i, here's a 0. 5 minus 2i, and my last 0 comes from this factor, negative 3. So there you have it. A lot of search for zeros there. Hope that's helpful. Stay tuned. Glad you were here, and we will see you soon.